Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about pericyclic reactions. So, what is pericyclic reactions? You know my friend, pericyclic reactions are any concerted reaction in which bonds are formed or broken in a cyclic transition state. Means electrons move around in a circle. I repeat, any concerted reaction. Concerted reaction means there is no formation of intermediate. So any concerted reaction in which bonds are formed or broken in a cyclic transition state. You know the transition state. Electrons move around in a circle. That is, there is a single transition state from start to finish in contrast to a stepwise reactions. You can see here concerted reaction and multi-step reactions. What is the difference in these two type of reaction? You can easily identify. Energy versus reaction coordinate, energy versus reaction coordinate. So in first case, starting material and product, there is a transition state, single transition state, and in another case, starting material, intermediate and products. So concerted reaction and multi-step reaction, this is the main differences. My friend, what is the properties of pericyclic reactions? Little if any solvent effect, no nucleophiles or electrophyte involved. Very important point, write it down. Little solvent effect, no nucleophiles or electrophiles involved in this type of reactions, and not generally catalyzed by Lewis acid. Highly stereospecific, often photochemically promoted. So these are important topic and important sentences related to the properties of pericyclic reactions. Now, electrocyclization reaction. What is the electrocyclization reaction? Linear conjugation or linear conjugated polyenes converted into a cyclic product. Pi bond converted into sigma and new pi bond in one step. The mechanism is not particularly surprising, but the stereochemistry changes depending on whether heat or irradiation, typically UV light, is used to promote the reactions. So my friend, if you go to the more basic, so such type of questions, so what are pericyclic reactions? The word pericyclic comes from how the electron flow round the outside of the ring. It is a type of organic reaction where the transition state has a cyclic geometry. You can see the expansions of this 6-member ring to 7-member ring. As I told you and previously explained, properties of a pericyclic reactions, they are highly stereospecific in nature. Now, what is stereospecific? I will talk later. That is a single stereoisomers of the reactant forms a single stereoisomers of the product. No electrophiles or nucleophiles are involved, not generally catalyzed by Lewis acid, often photochemically promoted, as you have seen. Now, classification of pericyclic reactions. Electrocyclic reactions, cycloaddition reaction, sigmatropic rearrangement, and group transfer reactions. So what is electrocyclic reactions? My friend, under the influence of heat and light. These two important words you keep in your mind: heat and light. A conjugate polyene can undergo isomerization. Here also another important term, conjugate polyene, can undergo isomerizations to form a cyclic compound with a single bond between the terminal carbons of the original conjugate system. You can look at this example. The name of this molecule, which is a conjugated polyene 3Z hexa 135 triene, and how it converted into the cyclohexaone-3-diene. So this type of conversion is known as electrocyclic reactions. Now the reverse process can also occur. This is also very important reverse process. In case of pericyclic, the formation of ring and breaking of ring to the open chain. So a single bond is broken and a cyclic compound yields an open chain polyene. For example, you can see cyclobutene and buta-1,3-diene. Now you can see the cycloaddition reaction. What is the cycloaddition reaction? A cycloaddition is a pericyclic chemical reaction in which two or more unsaturated molecules combine with the formation of a cyclic adduct in which there is a net reduction of bond multiplicity. Look at this reaction scheme. Types of cycloaddition reaction. First, Diels-Alder reaction. You can see the diene and dienophile. Diene, this compound contains two double bond at least, and dienophile one. And after combination and addition through the cycloaddition, cyclic compound you will get. Now the important type of reaction is known as sigmatropic reactions. What is sigmatropic reactions? Molecular rearrangement in which a delta bond atom or group flanked by one or more pi electron system shifts to a new locations with a corresponding recognition of the pi bonds are called sigmatropic reactions. So you can see the here concept 1-3 shift. One, you can see the positions of 1 and you can see the position of 3. So 1-3 shift of hydrogen in allyl system, 1-5 shift of hydrogen in 1-3 pentadiene system, and 1-7 shift of hydrogen in 1-3-5 heptatriene system. You know, this type of shift present in Cope rearrangement. This is also very important rearrangement of which is the example of pericyclic reaction, especially sigmatropic rearrangement. The Cope rearrangement is an example of 3-3. Here 3-3 is very important. You keep in mind what is the meaning of 3-3 here. So sigmatropic rearrangement, in this case the first atom of migrating group is not bonded to alkynyl chain. You can see the 5E hepta-1,5-diene converted to 3-methyl hexa-1,5-diene. So this 3-3 shifting is important here. In demonstration you can look at here, this 3 hydrogen is transferred to at position of the another 3. So this is the 3-3 sigmatropic, and generally we are saying this is the Cope rearrangement. Now for the beginner it is important to know that I in J, where I is 3 means in bracket it is written 3. 1 is I, that is the 3 of the migrating group which become bonded to the atom 3. So migrating group we are representing with the I and we are writing in the big bracket first, and the atom 3 where J is equal to 3 of the alkynyl chain. Thus, this is an example of 3,3 sigmatropic rearrangement. So, the migrating group is I, you have to write first, and where is the migrated, you have to write in the last, that is the J value. So, in bracket we are writing I and J. So, I is equal to 3 in case of co-rearrangement and J is equal to also 3 in case of co-rearrangement. That why we are saying 3,3 sigmatropic rearrangement. Now, group transfer reactions. This is also very important part of the pericyclic reaction. A group transfer reaction is a pericyclic process where one or more group of atoms is transferred from one molecule to another, and they can be sometimes difficult to identify when separate reactant molecule combine into a single product molecule. Unlike other pericyclic reaction classes, group transfer reactions do not have a specific conversion of pi bonds into a sigma bond or vice versa, and tend to be less frequently encountered. So, if you look at this example, like all pericyclic reaction, they must obey Woodward-Hoffmann rule. And you know the Woodward-Hoffmann rule is important rule we have to check in every pericyclic reaction. If it is not followed in the reaction, it means this is not the part of pericyclic reactions. Now, you can see another examples of electrocyclizations. So, electrocyclization we have seen earlier how the cyclization occurs. So, linear conjugated polyenes converted into a cyclic product, pi bonds converted into sigma, and new pi bond formed in one step. The mechanism is not particularly surprising, but the stereochemistry change depending on whether the heat or irradiation means light, typically UV light, is used to promote the reaction. So these two important words you keep in your mind, heat and light. So look at this reaction scheme. In presence of heat, the product is this one. In presence of light, the product is. These two products are different, not the same. So cycloaddition reaction, two linear conjugated polyene converted into a cyclic product in one step. Again, the stereochemistry of the reaction is remarkably reproducible. For example, 2 cis or Z alkenes, irradiation it gave these two types of products. Now, you can see this would be classified as 1,2 shift, 1,2 sigmatropic rearrangement, and this would be classified as 1,5 sigmatropic rearrangement. So, numbering refer to the number of atoms in transition state or either side of whether bonds are made or broken. Look at here, this example sigmatropic rearrangement reaction, a high level of stereochemical control is often observed, and this would be classified as 3,3 sigmatropic rearrangement or shifts. Now, Woodward-Hoffmann theory for prediction of the stereochemistry of pericyclic reactions. This is also very important. In cycloaddition reaction, the situation is highly different because two molecules are used and electron flow takes place from the highest occupied molecular orbital HOMO of one molecule to the lowest unoccupied molecular orbital of the other. The stereochemistry therefore follows from the wave function sign of the orbitals on each molecule. Consider the reaction of butadiene with an alkene, the Diels-Elder reaction, you just seen it. So in this process, the reagent approach each other in a phase-to-phase manner so that p orbitals of the pi system can combine with each other. The relevant orbitals are shown here. You can see the HOMO and LUMO. You can see the butadiene HOMO and LUMO. So in case of HOMO, LUMO is figure like that. In case of butadiene, and the symmetrical arrangement of HOMO, LUMO is like that. So the following combinations can be employed in the superficial cycloaddition reaction. In case of alkene, you check the LUMO, and in case of butadiene, check the HOMO. So this is the HOMO-LUMO gapping and formations of. So in both cases, the appropriate sign of the wave functions on the orbitals are matched so that the reagent can approach each other in face-to-face manner and also form bond easily. So in practice, it is usually the combination of diene HOMO with alkene LUMO which lead to product rather than diene LUMO and alkene HOMO. So electron withdrawing effect groups on the alkene lower its HOMO LUMO energy and improve the matching to the diene. In turn, this increase the reaction rate. Hence, electron withdrawing group on alkene generally increase the reactions rate, often very significantly, as might be predicted. Electron donating group on the diene also improve the rate by pushing the HOMO energy closer to the alkene LUMO. So look at here the energy difference between HOMO LUMO. Here you can see the differences. So more closely matched orbital give a greater energetic benefit when the combined. Hence the closely related butadiene and alkene represent the favored combination. When electron withdrawing groups are present on alkene, the benefit is even greater because the HOMO-LUMO levels are very closer, even closer. Lewis acid speed it even further. You can see here. Now del-cell radiation proceed in a superficial manner. The reagent add together is a fully matched face to face. So from here I will discuss in next class.